Hi everyone, Christian Aparicio here again to bring you another presentation on Nastran Solution 200. What I want to do with this presentation is show you the fundamentals of optimization and how that relates to structural optimization with Nastran. And here's what I have as an agenda. Again, we're going to go over what optimization is. I'm going to go over some very simple mathematical examples. These are all three-dimensional graphs that we're all familiar with, so I think this best communicates what optimization is. We'll then switch gears and talk about how to optimize finite element models with Nastran Solution 200. I'll make a definition of, or I'll state the definition of what size optimization is, and then we'll actually perform an example with a simple truss towards the end. This is part one of a 4-part series in the next 4 weeks regarding Nastran Solution 200. Today, the date is the 26th, I believe. In 1 week, we are going to have another presentation on automotive and Nastran Solution 200. In another week, we're going to have one for aerospace. And in the 4th week, we're going to have a presentation on sensitivity analysis with Nastran Solution 200. Again, these are happening every week for the next 4 weeks. This is all happening on YouTube Live. You can email me for a schedule of the upcoming webinars, or you can view my YouTube channel where I have these future events posted. One thing you'll see me use throughout this presentation is the Nastran Solution 200 web app. This is an application that runs on your web browser, and its main purpose is to take an existing Solution 100 PDF file. This could be Solution 101 for statics, 103 for normal modes, and so on and so on. And the web app will help you convert the file to Solution 200. And I'll explain more what that involves later on. Also, this is just a small glimpse as to the wide range of optimization training we can go over. There could potentially be over a day's worth of training. This is just a small hour of a larger training. And just in case you want any more support with optimization, I am here for that. If you want more training, if you want access to the web app, if you want guidance on a project of your own, I'm here to support you on that. And feel free to send me an email here, and I'll definitely get back to you on how to set any of this up. And now, to answer the big question, what is optimization? And before I continue, let me make a brief comment. If we have any questions or comments, feel free to ask a question in the chat box located to the right of the screen. Alternatively, you can send me an email. And at the end of the presentation, if time permits, I'll stick around 5 minutes to answer any questions you may have. And now let's go over what optimization is. I'm going to go over 4 examples. Let me go ahead and show you the first example. So let me go ahead and navigate to my desktop. And that was not what I wanted to do. If you remember back to calculus, the one thing we did a lot in calculus, we found the maximas and the minimas of multivariable equations. This is essentially what optimization is. Given a function, what is the maximum or the minimum? As an example, if you're dealing with structures, if you want to minimize the weight of your structure as much as possible, your function could be weight, and the variables could be structural dimensions of the structure. Then your objective would be to minimize or find the minima of your weight function with respect to those design variables. Here on the screen, I have a very simple 3-dimensional function. This plot that you see here is this function f. And maybe I should show you this example first. So here in purple is our original function f. Here in green is an initial or starting point. We are at 3, 4 for x and y. And we want an optimizer to find the optimum, in this case, the minimum. And here you could probably glance at this and know that the minimum is at 0, 0. When we give this to an optimizer, the optimizer will move steadily in different increments until it finds the minimum. So here if I zoom in and if I rotate this, here at 0, 0, you actually see the progression of the optimizer going towards the minimum of this function. This is a simple case. Let's now explore the case where we have a so-called constraint. Here, same function f, but now we're including a constraint g1. We are saying that g1 should always be greater than 1. And here, let's go ahead and look at what that looks like. So here in green is the function g1 equals to 1. The way our constraint is defined, our so-called feasible region, is everything outside of this ellipsoid. Everything outside of the ellipsoid will satisfy this inequality or constraint. Let's go ahead and look at what the optimizer does now. The optimizer will go down towards the global minimum, as you see here, but as soon as it encounters the constraint, it begins to move along the constraint. And here, let me rotate the model and show you why it continues to move down the constraint. If you notice that when it first hit the constraint here, there was still opportunity to further minimize the objective function f. And that's exactly what it did, ultimately leading to the minimum at 1, 0.05 with an f value of 1.01. So again, this is what optimization is. If you have a function f, design variables x1, x2, x3, x4, etc., etc. If you have a constraint, such as the one we showed here, optimizers will seek a minimum or maximum for your given function. And before I actually demo you the procedure and how to do this in Nastran, there are 3 things I want to define for you. The main idea on this slide is actually the optimization problem statement. This is a very critical thing you should have before you perform optimization. It's composed of your variables, your objective, and constraints. Your variables, in this case, were the variables x1 and x2. The objective, this would be a function in terms of those variables or constraints. G1 in this example was a constraint. Later on, where you're dealing with structures, your objective function might be weight, or it might be displacement. Those responses, if you will, are dependent on design variables such as structural dimensions, material properties, and so on and so on. Your constraints, you might have a stress constraint. The stress and tension can be no greater than 25,000 psi or 10 megapascals. And now that I've defined that, let me go ahead and actually show you how to do this in Nastran Solution 200. We are going to replicate this example that you see here on my screen. We're going to let Nastran find the minimum for this function given this optimization problem statement. So let's go ahead and get started with that. The first point may be a PDF file. So here, I'm creating a new folder on my desktop, and I'm going to go ahead and open this PDF file or DAT file. This DAT file you may have created in your pre-post processor, such as Patran. It could be some other pre-post processor you have. We're going to copy all of this, and we're going to convert this text to Nastran Solution 200. Let's go ahead and paste the text in the Nastran Solution 200 web app. And then we'll go ahead and identify designable properties. You'll notice that these 2 properties have current values of 3, 4. These are the same x and y values that we had here in this original example. So let me go ahead and show you what that looks like. So here in red is the initial starting point 3, 4. Let me translate the box so you see that. So here's our original 0.3, 4. So let's go ahead and create our design variables in the web app. We'll go ahead and select the plus icons, and in the next table, you find our newly created design variables there. And that's it. That's how simple it is to create our design variables. Let's go ahead and move on to our objective. Here, our objective is a custom equation for the objective. So we'll go ahead and switch to synthetic objective. This box that you see here is where I can type in my function. If you notice back in the variables section, the variables have labels x1 and x2. These are the same variables I can type in here. So I can type in x1 squared plus x2 divided by 2.0 squared. And now let me confirm this is actually what I want to optimize. And here, this function should actually be x2 squared. And then, of course, I want to minimize this. So x1 squared plus x2 squared, that would be our big purple function in this graph. So that would be this here. Let's go ahead and now create our ellipsoid design constraint. And let me look at the equation real quick. X1 squared plus x2 squared. Let's go ahead and type that into the web app. So after you define your objective, let's move on to the constraints. Here, if we scroll down a little bit, there's a section where you can create your so-called synthetic constraints. Click on the add to create one custom constraint. This is where we'll type in x1 squared plus x2 divided by 2.0 squared. And here we said that whatever x1 and x2 are, it should always be greater than 1.0. And let me look back at the optimization problems statement and make sure that looks good. Okay, so far so good. And one last thing I have to do for the constraints, I have to create a constraint group that's applied to all the subcases. So in step 3 of the same constraint section, click on add all constraints to group. And then we'll go ahead and select all subcases. And there we go. Now we can move on to the exporter. Let me show you the original BDF file. Here on the right, you see our BDF file was originally solution 101. Now it's solution 200. It's added the analysis, the design objective, and the design constraint group pointers. The 9 million is pointing to different entries, and so on and so on. Here on the right, I have the output for the design variables, the design objective, and the design constraints. And you'll notice that throughout the use of the web app, the application will automatically generate and maintain these bulk data entries for you. So there's no need to manually type these out or create an elaborate script or use an elaborate separate application for this. The web app's purpose is just for this. So now, let's go ahead and download local copies of these files. So download the converted BDF file and the design model. And on my desktop, I'll create a new folder called optimization directory. So to optimization directory. This is where I will put all of my optimization files to perform the optimization. So let's go ahead and move those two files there. And now let's go ahead and make one modification to this example. I'm going to delete these two entries here, dbpro1. And now let's go ahead and run Nastran. And select model BDF and run this optimization example. Again, as a reminder, if you have any questions or comments, feel free to send me an email and I definitely will get back to you with an answer. And now let's go ahead and see where the optimization is. It's still going on. After the optimization is complete, the first file you want to inspect to make sure you've had a successful optimization is the F06 file. So let's open that file in Notepad. And at the very bottom, search for this section, Summary or rather it's a section, summary of design cycle history. If you scroll a little further down, you'll find this table. Under this table, you should find this message: run terminated due to hard convergence at an optimum. So let's define what hard convergence is. This basically means that the optimizer has leveled out in finding a minimum. Here, if we look at the optimization path, you can see that the values for F were slowly converging to a value of 1.01. This is what is meant by convergence. And now, what does optimum mean? Optimum means that it essentially found a trough or a maximum, or rather a minimum or a maximum point. Here you can see that the optimizer has moved downward along this curve, and then it could have continued on, but then it would start to increase. So this, it's decided, is the local minimum, and that's what's meant by optimum. It's either found the minimum or the maximum. Let's go ahead and digest what some of these numbers mean in this table, if you will. This column that you see here is reporting the value of your function or your objective function. For example, at the very beginning, at 3, 4, we had a value of f equal to 25. So here, if you were to plug in 3 and 4 to this equation, you would get 25. And then if I zoom out and rotate this graph, you'll find out that the starting point was actually 25. So here, 25. The next point at, let me see if I can zoom in on this, 1.5, 2 had a f value of 6.25. So here you see 6.25 reported, and then you see every other value for the objective reported here, ultimately landing on a f value or objective value of 1.01. This next table reports the value of your design variables. Again, we started at values for x1 and x2 of 3, 4, and then went to 1.5, 2, and then at the end we ended up at 1, 0.05. There is a way to view these results in Excel, and I'll demonstrate that in my future demonstration in a few minutes. So now let's go ahead and go back to our presentation, and that is your very first example with optimization with Nastran Solution 200. And then again, if you have any comments, questions, if the video is choppy, if the audio is cutting in and out, let me know in the chat box so I can definitely address that. Now let's go back to the presentation and let me show you a few additional examples before we move on. So if we go back to our graphical examples here, this first example I showed is known as an unconstrained optimization example. Here, the optimizer was allowed to freely go to the minimum without any sort of hindrance or constraint. The second example is known as a constrained optimization example. Here, the optimizer was not allowed to freely find the minimum. We impose a constraint here represented by the green ellipsoid, and you can see what happened with the outcome. There's also another example, side constraints. Let's suppose you wanted to impose limits on your design variables. Here, for example, I wanted to impose a limit on x1, saying that x1 should be between 1.5 and 5, and x2 should be between -5 and 5. Here in dotted lines is what the side constraints will look like. And here you can see what the optimizer has done. Number one, the feasible region is the area that satisfies all the constraints. For the green ellipsoid, that's everything outside of the green ellipsoid. With the side constraints, that's everything within the box. So the feasible region is essentially this dotted line region. And here, as you can see with the optimizer, it's made an attempt to go to the global minimum here, but as soon as it encountered one of the constraints, here the side constraint, it still moves along the side constraint until it reaches the minimum. And now for my fourth example. This example you might encounter a lot, so I figure we should definitely spend some time on this. Sometimes when you inspect the F06 file, you may have a different message that says run terminated to best compromise infeasible design or something along those lines. This is what the message means. Let's suppose we have this optimization problem statement. We have the same function f and the same g1 function. We introduce a new g2 function represented by this red ellipsoid. The constraints are as given. The final x1 and x2 value can be any value within this green ellipsoid, which is another way of saying g1 less than 1. x1 and x2 can be any value within this red ellipsoid, which is another way of saying g2 is less than 1. This is what the optimizer does. First thing to notice, there is no solution that satisfies both of these constraints. A solution in the green ellipsoid cannot possibly be in the same red ellipsoid at the same time. What the optimizer will do, it will land in the middle between the constraints, and hence the file will report best compromise. It's try to find a solution that is in between your design constraints. And it's infeasible because here the infeasible region is everything outside of these ellipsoids, so that's your infeasible region. How do you fix such a problem? You might encounter this if you're trying to impose stress constraints on your structure. It may be the case that the stress constraints are so strict that there's no region that satisfies your objective of minimizing your objective function. So how would you handle a situation like that? What you can do is expand, relax, enlarge one of your constraints. Here is an example. We took the second constraint, the red ellipsoid, and we've expanded the design constraint region. Now that there's an overlap between both constraint groups, we have a so-called feasible region. And here in orange is what the optimizer does. It can now move towards the minimum. It can find an optimum in this narrow strip of a feasible region. And if we rotate this, we find that the minimum was actually found, as you see here, in the X. Again, this might be a common thing you see when you first start doing optimization. Maybe you're trying to satisfy all of your stress constraints. You then find in your F06 file this message that says run terminated due to best compromise and feasible design. To remedy that, just relax your constraints, expand your constraints until you have a small strip of feasible region where you can find the actual minimum. And now let's go ahead and close this and move on to the next portion of our example. So this was a very introductory section for optimization. Let's go ahead and move on to actual structural optimization with Nastran Solution 200. Here in this example is where defining what size optimization is. Here on the left, I've got a finite element model of a thin-walled cylindrical structure. By itself, there's not too much that's impressive here. And just bear with me while I look at my streaming settings. Okay, perfect. Again, if the video or the audio cuts out, please let me know so I can definitely address it. I know given bandwidth, it might go up and down. Back to the presentation. So here's our structure. We zoom in on it and there's nothing too impressive about it. For example, the two-dimensional yellow elements here, these actually have a thickness associated with it. And it's not until we specify parameters to these elements that they finally have significance. Again, we applied a thickness parameter to the two-dimensional elements. We specified beam cross-section dimensions to the line elements that you saw a moment ago. In size optimization, it's also known as parameter optimization. It's the process of setting these parameters as design variables. I can set the thickness and the beam cross-section dimensions as design variables, and this is what size optimization is. For the remainder of this presentation, I will be talking about size optimization. And now let's go on and discuss our first example. We're going to perform a very simple optimization example of the structure. It's a fixed rod fixed on one end, and we're pulling on it with this load on the other end. The cross-section is circular, and here's our optimization problem statement. We're going to let the radius of the cross-section vary. We're going to minimize as much as possible the weight of this rod, and we're going to impose a design constraint saying that the axial stress for these elements cannot exceed 110 megapascals. So now let's go ahead and discuss what the process is for this in Nastran Solution 200. Before I go ahead and do that, let me point out that we are doing nothing different from before. Before we had design variables x1 and x2, we had an objective function f, we had a design constraint 1 is less than g1 equal to its expression. We're doing nothing different. Our design variable x1 is representing the radius of the cross section. Our weight function, or our objective function, is the weight, and our constraint function is the axial stress in the elements. Again, we're going to use the Nastran Solution 200 web app. This is going to take our 100 BDF file and convert it to Solution 200. And now let's go through the procedure of doing that. This is a very thorough procedure, so I'm going to show you how to convert the file to Solution 200. I'm going to show you how to view results inside of Excel, Patran, and ultimately how to update your final BDF file with the new structural dimensions. So let's go through the process of that. Here in Patran, I have the example already loaded. Maybe it might be worth looking at the axial stress in this example. So let's go ahead and look at what that looks like. One thing you'll notice with optimization, the optimizer will vary some of the dimensions, obviously, and it will do this until it encounters the minimum, or it encounters a design objective that limits the optimization. In this example, what you'll find happen, it will steadily try to reduce the mass of the structure, so it will vary the radius. It then will hit the limit of the constraint of 110 megapascals. Our initial design, as you see here, it's currently at 51 megapascals. You're going to see the radius shrink, but the axial stress actually increase until it hits the upper limit of 110. So now let's go through the process. You may be at the starting point. You may have already created your model in Patran. You now want to perform optimization. Let's go through the process. I'll create a folder called initial design, and then I'll paste the file from Patran here. If we open the file, we find that it's a solution 101. There are definitions for the elements, the material, the loading, and everything else. We'll go ahead and go to our web app and start a new session. You can refresh the page, and we'll select all the text here, and we'll copy that and paste it here to begin the conversion process. When you click Identify Designable Properties, the web app will identify all the parameters that can be set as design variables in your model. Here, I want to look for dimension 1, which is the radius of the cross-section, and I'll go ahead and select the plus icon here to set it as a design variable. When you do that, the next table shows you the new design variable. This is where you can supply your side constraints. So if you want to limit the radius, for example, you might type in 0.001. Here, this lower bound is important. You don't want to have a radius that's lower than 0. That's not possible. That could potentially actually cause an issue during the optimization, where it'll state you've made an error, you've supplied a negative value for the radius. For the upper bound, I think we had, I don't think we impose, oh yeah, we did impose an upper limit of 100. So let's go ahead and type that in right here. And that completes the creation of our design variable. Let's go ahead and focus on our objective. Here on this list, you have a very long list of objectives you can set. And here I'm just focused on the weight. So let's go ahead and select the weight. And we'll want to minimize this. And now for the constraints. Here, I'm going to look for the stress constraint. So let's go ahead and move to page 2 and click on the stress one time to create a constraint here in the next table. We'll type in P bar L. We'll type in property 1. And this property is the property being used for P bar L here. So each element in this model is being set to a radius of 0.025. And now for our upper limit, 110 megapascals, so that'd be E6. And now for the stress item code. We're dealing with rod elements. These rod elements will produce various types of stresses. They'll produce axial stresses. They'll produce torsional stresses. They'll produce other types of strains. They'll produce torsional forces or moments. They'll produce axial forces, and the list goes on and on and on after that. What the stress item code is, it's a number that identifies and singles out a specific quantity. To get a list of what the items codes correspond to, you can refer to the Nastran Quick Reference Guide. There's a chapter called Item Codes. Here we go to element stresses, that is. This is where you find item codes for those various stress quantities. In this model, we're using C-bar elements, so we have to refer to the C-bar 34 element here. And we're looking for the axial stress, and here, N6. Item code 6 is my axial stress for this element. So I'll use the 6, and I'll type that into the web app here. And there we go. We've imposed stress constraint for axial stress for P bar L1 with an upper limit of 110 megapascals here. Before we move on, let's go ahead and create our constraint group. I'll manually create a constraint group by clicking this plus icon. And then here, if you notice, this constraint has the label of R1. We'll go ahead and type in R1 here. And then apply this to all subcase, and that completes our new constraint. If we had other constraints, we can simply type in R2 here, R3, and so on and so on. But here I'm just dealing with R1, so we can go ahead and type in R1 here. In our exporter, we are doing, or rather the web app has converted this to solution 200. We're doing a static optimization. There's a pointer for the objective and the constraint group. Here on the right is our design variable, our objective, and our constraints. And now I can download both of these files and go on to my optimization. Again, if you have any questions, comments, feel free to leave me an email or send me or drop me a message in the chat box, and I'll definitely get back to that. And here I'm just making a new directory called the optimization directory. We'll drag and drop those two files there. And now we'll start Nastran and perform our optimization. And bear with me while I go ahead and do that. And so in a moment, we'll go ahead and inspect the F06 file. And the one thing I want to show you is how to view these results inside of Excel too. So let me go ahead and find my Excel template here. I'll go to my okay, perfect. So here, let's first open the F06 file and make sure we have the successful message run terminated due to hard conversions at an optimum. Here we have the message run terminated due to so on and so on. So perfect. We've had a successful optimization. Let me go ahead and move this to the right and the same optimization working directory, a comma separated value or CSV file has been created that you can open in Excel. So let me go ahead and do that. I'll move this to the left. Here you'll see the same values reported in the F06 file. You'll see values reported for the objective, as I'm highlighting on the right, are also reported here on the left in the CSV file. The design variable history reported on the right is also reported in the CSV file on the right. And the great thing about this is that now I can open Excel and manipulate the answers or the plots to my liking. So here I can select all these results and paste them in my template. And the template will go ahead and update the graphs for me. And here you might want to manipulate the column headers as an example. So here I'll modify these column headers. I'll say that this is the initial design, and then this is the optimized design. So this example went through 1, 2, 3, and 4 design cycles. So let's go ahead and update the plot here with these horizontal data labels. And so here we started with an objective or mass of 5.3 and we ended at a mass of 2.45. Here on the right is the history of my design variables. Here we only had one design variable, x1, which corresponds to the radius of the cross section. I could do the same thing as before, just change the column headers and so on and so on. So that's how you view the results in Excel. Let me go ahead and close out of these. And now 2 last things. So here in Patreon, we have the old initial design results, if you will. Let me go ahead and detach these old results. In the same working directory for optimization, there is a new result file that was created. Let's go ahead and attach that. This result file has 2 sets of results. The first result is for the initial design. So here, like before, we have 51,000 megapascals for the axial stress. The second set of results is the structural results for the optimized model. Here you can see 2 markers in the name. One is called D0 for design cycle 0 or the initial design. This is design cycle 4 or D4 for the optimized design cycle. If we select this design cycle and plot our results, you'll notice one thing. Our new stress is now 110 megapascals. So what the optimizer has done, it has minimized the radius of the cross section until it found the minimum and it exceeded one of the constraints. Here it's right at the edge of the upper limit of the axial stress constraint. So this, you always want to look at your results in your pre-post processor just to validate that your constraints have in fact been met. Sometimes if you're configuring your constraint or your design variable, there might be an error that was made and it will show up here in your validation step in your pre-post processor. So now the last thing we want to do. At the very beginning, we started with this PDF file. This was the original model with the original radius of the cross section of 0.025 meters. But now we have to update this value. How do we do that? Let's create a new folder called 3 Optimized Design. 3 Optimized Design. And then I'll make a copy of the first PDF file. And then I'll paste it in this new directory. And then we'll go ahead and open this in Notepad and we'll make the edit. In the second optimization directory, there's a PCH file or punch file that was created. Open that in Notepad also. And here, let me take some time while the machine keeps up. I'll move this to the right. Here on the right is the original PDF file. Again, the P-bar L entries was specified as being cross-section. And here we have a value of 0.025, which is the old value. The optimized value is 0.017, but then we have to update the entry on the right. What you can do is just simply copy the one on the left and paste it here on the right. And there you have it. That's how you update the original PDF file, by opening the punch file, copying over the new entries, and saving your old PDF file. And now this PDF file that you have in the third directory is your new optimized version. So now let's go ahead and open up my PowerPoint and summarize today's presentation. So we've gone through what optimization was from a mathematical standpoint. As you saw, it's a very intuitive thing. It's just a matter of finding a minimum or a maximum for a given objective function. You can impose constraints, like I showed earlier in the first example. We then switch gears to Nastran Solution 200. We went over what size optimization is, which is essentially finding a parameter in your model, setting that as the design variable, and then minimizing a weight function and imposing a design constraint function, say on stress or displacement. We went through a very brief example, very subtle and very simple. What I wanted to show there is what the procedure was in converting your Solution 101 file to Solution 200, how to view your results in the F06 file in Excel, how to validate your structural results in Patran or your own pre-post processor, and then how to convert the old PDF file to the new version with optimized parameters, and so on and so on. And then just to slow down this presentation and call it an end, again, this is part 1 of a 4-part series this month on Nastran Solution 200. You can view each presentation on YouTube Live, where I'll walk through more elaborate examples. Next week, I'll do a more elaborate example on automotive. If you're an automotive engineer or a student who's thinking of being employed in the automotive industry, this would be a great example for you. There would be 2 relevant examples for automotive presented, and I'll talk more on how to use Nastran Solution 200 for that. After that, there will be a version of that presentation, but it will be for aerospace. So I'll be presenting 2 relevant examples for the aerospace industry. And then after that, on the 4th week, we'll talk about sensitivity analysis. This is a critical part of optimization, and this I'll leave for last in approximately 4 weeks. Again, you can find the latest schedule at my YouTube channel, or you can send me an email at christian@theengineeringlab.com, and I definitely will get back to you on that. Just in case you want more training, more guidance on a project of your own with Nastran optimization, or if you want access to the web app, again, you're always welcome to email me. With that, I want to give you all a big thank you for being with me today. If you have any questions, I'll stick around for 5 minutes and then I'll answer those. If not, I'll go ahead and reply to your email and then get back to you like that. And then here I have an example, or rather I have a question in the chat box. Is it possible to do all this optimization models other pre? Can you re-ask your question a little differently? I quite didn't understand all of it. If you do that, in the meantime, I'll go ahead and answer that. Can you do this for other optimization examples? That's a very great question. And let me go ahead and open. Let me see if I can find it. My Introduction to Optimization Guidebook. So I'll show you what this topic or this presentation applies to. There are a lot of optimization examples out there. This presentation focuses on just one, which is size optimization. So let's go ahead and scroll down and find, okay, here we go. There are many types of optimization out there. There's topology optimization, which is analogous to a sculptor chiseling material away from a structure. There's shape optimization, where you let the boundaries or the profile of your solid vary, such as the before and after you see here. There's topometry and topography optimization. These 4 are not addressed by the web app. The web app addresses size optimization. And to answer the question inside of the chat box here on the left or right, again, this web app is exclusively for size optimization. If you want to do any of these other optimization types, you will have to use a pre-post processor out there. And then I think that handles that question. And then if there are no more questions, again, I'll stick around for a few minutes. I'll leave the slide up there so you can write down my contact info. And again, a big thank you to everyone, and I look forward to having you in my upcoming presentations.